Hi everybody, and welcome to Muddiest Points mini lecture. I'm going to be talking about bitwise operations and GPIO. But first, I had a weird question. How do I get a beard like yours? And the short answer is be male and prone to hairiness. That helps a lot. Never shave, only trim. The fact is, I've had this beard since I was in high school. I'm 31 now, and my wife has never seen me without it. And I asked her if she ever wants me to shave it, and she says she's a little freaked out by what's hiding underneath. So, that's the answer to that question. I got some good questions, non-weird questions, about bitwise operators. We're going to review those very quickly, and then I'm going to go over the GPIO stuff very rapidly and try to get you a little more information and do a couple more examples on how all this stuff works. First off, the bitwise operators, we've got, of course, the AND or ampersand operator, the OR, pipe operator, complement, tilde, XOR, caret, shift left, left wakas, two left wakas, shift right, two right wakas, right? And each of these, the AND operator takes two numbers and does a bitwise AND on them. So if I've got x is equal to 12, which is 1100 in binary, and y is equal to 5 or 0101 in binary, I can find the AND of those, the bitwise AND of those two numbers by doing x and y, z is equal to x and y. Right? So if we're looking for z and we want to know what z will be, we just plot these out, and it goes column by column. So we look at 0 and 1 gives us 0, 0 and 0 gives us 0, 1 and 1 gives us 1, and 1 and 0 gives us 0. So we end up with the binary value of 4 stored in z. For the or pipe operator, we do the same thing, x or y. And we go column by column. So 0 or 1 is 1, 0 or 0 is 0, 1 or 1 is 1, and 1 or 0 is 1, right? Which gives us 13 as a numerical value. The XOR is a little bit weirder. It's the exclusive OR, so it results in 0 when the two bits are 1 and 0 when the two bits are 0. So, for example, in our thing here, 0 XOR 1 is 1, 0 XOR 0 is 0, 1 XOR 1 is 0, and 1 XOR 0 is 1, right? Which is 9 in a numerical value. Now we've got the two shift operators. So here we do y, left waka waka, 2. And the 2 here is a constant, or it could even be a variable, that defines how many bit places, how many bit locations we want to shift the numbers, the bits in y to the left. Right? So for instance, I've got y lined out here, and we're shifting it left 2. And what this means is that all of the bits in y are going to be shifted left to 2 and copied into z. So what we end up with is all of the bit patterns look like this. So 1 is going to end up here, this 0 is going to end up here, and all the other ones, because they end up farther out on the end of the representation, disappear. And that we're only looking at 4 bits here. If we had more bits, they wouldn't go away. But notice that the 2 upper bits of our variable will be shifted out. And in these empty places, we're going to replace them with 0. So we end up with 1 and 0 here, and we shift in zeros, and that gives us a numerical value of 4. The right shift just does the same operation in the other direction. The right shift operator in this case is right wakas, and the 2, or constant, the number on this side, is still the number of steps. So we won't move the x to the opposite position. They don't flip around. This is, the second number is second variable is always how many spaces to move it. And again, the numbers that get shifted out just get cut off, they disappear, and we shift in zeros into the, in this case, most significant position. So we end up with 1, 1 here, and zeros on the top, which gives us a numerical value of 3. Now to apply these things to stuff that we're going to be utilizing, say we want to set bit 3 of an integer y. What we've constructed is a mask, what's called a mask, or it's a number that has the bit set, only one bit set, or one or two, or only the bits that we care about, set in the number. So in this case, 0x8 is 100 in binary, and we call this a mask because we're masking out only the bits we care about, right? So here y is equal to 5, or 0101 in binary, and to set the bit 3 of the y location, we OR them together, right? So what happens is we do 10 is 1, 00 is 0, 10 is 1, and 01 is 1. So you can see it's the exact same number, but only the bit that but the only difference is that the bit we care about, the bit set in the mask, has changed from 0 to 1. If it was 1, it wouldn't change, so we know that no matter what the value is here, we're going to end up with a 1 in that location, and all the other bits are untouched. And there's a couple of methods to construct the mask or do the operation. Here's an in-place OR, and here's using a bit shift. It does exactly the same thing. We end up with the exact same value. Now say we want to clear bit 2 of an integer x. In this case, x is our 12, and we're going to be clearing bit 2. So in this case, it's this number right here. Remember that the bits are 0 based. So this is bit 0, bit 1, bit 2, and bit 3, rather than 1, 2, 3, 4. Now, the mask in this case is the opposite of what we is the opposite. We want to have 1s in all the locations we want to preserve and a 0 in the location we want to clear. So in this case, bit 2 is this one right here, and in hex this is B or 11 in decimal, right? So this mask is inverted. It's kind of we could call it a negative mask or something like that. But the point is that what we want to clear is 0 in the mask. And the way we do that is we say x is equal to x and the mask. And in this case, we do an and we end up with a 0 and a 1 maps to 0, 0 and a 1 maps to 0, 1 and a 0 maps to 0, 1 and 1 maps to 1. So you can see that the only things that have changed are the stuff that we care about. Once again, in this case, we've cleared bit number 2 to give us 100, which is 8 in numerical value. And we can use these same set and clear methods to determine if statements and things like that, just like we went over in class. If you want more information and examples, you can go to these two links, which I'm going to post in the video description. This one talks about applications in game development and has a bunch of good examples of the bitwise operations. This one has a more general description of how we do things in the bitwise using the bitwise operations. Now, the GPIO stuff. Everybody was kind of confused. I had kind of a scattered thing. It was a lot of information, and I wanted to make sure I got some things clear. For one thing, I got a question, what is the PAR, port, and DDR registers? What do they mean? PAR means pin assignment register. It determines the function of the pin, whether it's a GPIO, whether it's an output of a PWM generator, input to timer, things like that. The point is that we've got so many peripherals and so many capabilities on the processor that we would need hundreds or even thousands of pins to be able to handle all of the I/O that we could possibly do. We only have 144 pins, so we have these pin assignment registers that allow us to set the function of the pin and choose among whether it's a GPIO or a PWM generator or an input to the timer or whatever else it could possibly be. Then, so say we set the pin as a GPIO using the pin assignment register. Then we have to determine whether or not the pin is an input or an output as general purpose I/O. Right? So we have a data direction register, or DDR, and this determines whether the pin is set to read as an input or write as an output. If we can write to it, then we can set the actual voltage on this physical pin to either 3.3, which is high, or 1, or 0 volts, which is 0 in binary. And we do that through the port register. It holds the current state of the pin. The port register for each of the different ports holds the current state of the pin. If the pin is output, set as an output by the data direction register, then we can set the state of the pin through the bits of port. If we set a 1 in a bit of port, the physical pin corresponding to that bit goes high. It goes to 3.3 volts. If we clear it, it goes to 0 volts. If the pin is sent as an input, we can read the bits of port and see how the pin is being driven. If it's being driven high, it reads as a 1. If it's being driven low or 0, it reads as a 0. In the lecture, I wanted to show you how the physical pin is configured so that we can switch between all these different options and look at how the system works and give you an intuition of what these different registers mean. So here is the PAR register, and this is the first one we want to modify, because what it does is it selects among the different outputs or the different inputs for the physical pin. It determines what is going to drive. It could be if PAR is 00, that means it's general purpose I/O, and we can use these registers to control the physical state of the pin. If it's set to 1, then it's whatever the pin's primary function is. If it's set to 2, it's whatever alternate 1 is. And if it's set to 3, it's whatever alternate 2 is. And these could be anything. It depends on what the system is configured for, and different tables will tell us information about what the primary and alternate functions of a physical pin are. Then the PN DDR, or the DDR bit, tells us what the data direction is, whether or not we control the pin using the port, or whether the pin is updated by the external world. And basically it switches the pin between these two buffers. This is the output buffer. If it's true on this line, then it allows the internal system to control the physical state of the pin. Basically, this drives it. We can drive it high or low. If it's an input, then the system reads whatever it is and allows the outside world to drive it high or low. And basically, it's which direction. If DDR is 1, then it is an output pin. If DDR is 0, then it's an input pin, and we take it from the outside world. Now, each of these physical pins has an associated bit. So, for instance, physical pin TC0, port TC0, bit 0 of port TC, has 1 bit of 8 that all configure it. We arrange these things into ports. Every port has 8 bits in it. So all of these physical pins and their associated controllers all have the same, all share a register, basically, 1 byte that we can treat as a whole, right? So port TC as a whole, we can control bits 7, 6, 5, 4, 3, 2, 1. And how those are connected is dependent on some information we'll look at in a minute, right? So we see this byte all together. Now this byte is part of the overall memory. It's part of here, port TC is inside of the overall memory system. So if we go up, we see port TA, a reserved byte, and then port QS, and then there's port UA, and all the other ones, and it goes on and on from here. And each of these has a location in memory, and this is offset from IPS bar. And what IPS bar is basically just a register that defines where the peripheral system exists. And we can actually move it around. We don't want to, because that screws with all kinds of things and it's kind of scary. But just know that IPS bar is set to 400_000, right? So these offsets are basically the mapping from the start of IPS bar, where the peripheral system starts on the processor. So these are our addresses. To find the actual total address, we just take the number that's given in the memory map and add it to 4000000, right? So, given a pin, how do we find the address of the registers and what bits to set and clear? There's a pretty simple process. There's about 4 or 5 steps here. And basically it starts off with, we look at the data sheet. We look at the pinout. In this case, we're looking at the package 144 LQFP on page 15. And we find the name of the pin. So if I give you a pin number, you go find the name of the pin. Then, using that pin name, we look in the reference manual on table 2.1 and find the function name, the quaternary function in this case. And this gives us which port that particular pin belongs to. Also, which bit of the port that pin belongs to. And This will give us most of the information we need to control the thing, because we know that we need to find the associated registers, the PAR, the DDR, and the port bits. So we find those in the port memory map, which is in Chapter 15, Table 15-1, or the register descriptions in 15-.6. Then given the offset, we add the value of IPS bar, which is this number right here, and that gives us the total address for each of the registers. Then we determine the bit functionality in the register description. So we look at the register descriptions in Chapter 15.6, and at the end of each section it tells us what the bits mean. We know where the bits are, what the bits mean, and from there we can write code that does it. So let's do an example using pin 108. The first thing we need to do is look up the name of the pin in the datasheet. So here in the datasheet, we're looking at Figure 2, which shows the configuration for the 144 LQFP, which is the device that we're using. And we can see that pin 108 is called FEC CRS. So that gives us the name of the pin, and that'll tell us, give us the information we need to find out what port that particular pin belongs to. So now we're in the reference manual, and we're looking at Chapter 2, Table 2.1, the Signal Descriptions chapter, and we're looking up the pin name, the primary function, to find out what port it belongs to. So we go looking down the column and we see this is FEC CRS, that's the pin we're looking for, it's pin 108, and the GPIO port that controls it says PTI 1. So that means it's this particular pin, this particular physical pin, is part of port TI, and it's controlled by bit 1 of port TI. So that's enough information that we can go to Chapter 15, the General Purpose I/O, and register descriptions, and find the addresses to the PAR, DDR, and port registers. Here in Chapter 15 of the reference manual, we want to look at Table 15.1. This has the description of the listing of the memory that controls all of the general purpose ports. In this case, we're looking for anything related to TI. So here's port TI at location 10.4. Here's DDR TI at location 10.1C. And down here is PTI PAR at 10.64. And what these numbers are is not a complete address. It's the offset from ISP bar. If you look down here at the footnote way at the bottom, the register address is the sum of the module base address and the base address offset. So these gives us the offset, and we need to know what the module base address is. And it's a thing called IPS bar, which stands for Peripheral System Base Offset Base Address Register. And it's a thing that basically defines where in memory these components, the control registers for all of the peripherals, start. In this case, it's 40000000, right? And we just add that number to all of these offsets to get the total address. Next, we need to look in the register description field to find what these things do and what the bits do. So here at the top, we're in the register description chapter 15.6, and we're looking through to see anything related to port TI. Oh, there's a typo. Good job, Freescale. And we see that port TI is at 10004, and we know that we're looking at bit 1, that's the bit that controls our particular pin that we're interested in. So we know that to the port bit that's associated with that pin is at location 1. Now what does it mean when we change that bit? We can look down at the end of this section and there's a description about what the fields do. So if we put a 1 in that location, the output on the physical pin is a logical 1 or a high voltage. If we put a 0, the output is a logical 0. And now we're looking at the data direction registers. We can see we've got DDR TI here at 1C, and we're looking at bit 1 of DDR TI as the one to control it. And what does it mean to have this bit set or clear? Again, if we look down here at the bottom of the chapter, we see that setting it configures the pin as an output, and clearing it configures it as an input. If we go down to the par bits, go past the clears, the pin assignment registers. We're looking for PTI par at location 64, and we can see that PN par 1 is the bit that's going to control our particular pin. And if we go to the description fields, we can see that if we set the bit to 1, it assumes the primary function, but we don't want the primary function. The primary function in this case is FEC-CRS. We want it to be a general purpose I/O pin, so we clear that particular bit. So first, let's recap. We found the name of the pin in the datasheet. Then we found the GPIO function name, PTI1, from the reference manual in Chapter 2, and that gave us the names of the, basically we could figure out that PTI par1, DDR-TI1, and port TI1 were the bits that we needed to control in order to turn the bit into GPIO using the pin assignment register, turn it into an output using the DDR register, and then we can set the bit the pin to high using the port register. We found out the addresses by looking in Chapter 15 of what the individual registers are. So here, register for PTI par is at 1064. We add the IPS bar value to get this value for the actual location of each of the registers. Then, using that information, we looked at what the bits mean. So we're looking at bit 1 of all of these registers, and we need to clear PTI par, bit 1 of PTI par, to set it as GPIO mode. We need to set bit 1 of DDR-TI to make it an output, and then we need to set bit 1 of TTI to make it high, or clear it to set it low on the physical pin. So here's a code example. This is doing it the hard way, and I'll show you an awesome, easy way in just a second. The first thing we need to do is define the locations of our registers. We do that by using the data type unsigned char, because these are 8-bit registers, and it's a pointer. This is a memory location. It's a pointer. So it's not the actual value of the register. It's just a location in memory. So we use those numbers that we calculated to define the locations of our 3 registers. So these 3 registers all point to locations in memory. To modify that location in memory, we have to dereference the register, and then we can do whatever we want to it. So the star here dereferences the register and allows us to access the memory at that location. And we just do the same things that we did in the binary bitwise arithmetic section to clear and set bits. In this case, I'm clearing bit 1 of PTI par, or PTI par 1. Here I'm setting DDR-TI1 using the OR equals and a mask. Then I'm setting port I1 using OR equals and a mask, just like that. Right? Now, here's the easy way. It's so awesome. Include support common.h. Rather than having to go through and calculate all of these addresses, it does it for us. So all we have to do is reference the different registers, and it defines macros for us for dereferencing, so we just we can treat it like a variable. We don't have to do anything special. So here I've got the name as defined by support common.h. Is basically MCF, GPIO, PTI par, and then it even lets me define, it even defines for us what bits are there. So in this case, I want to set, I want to clear bit 1 of PTI par. I don't even have to calculate the mask myself, it's already done for us. So that's, you can see that each of these are built the exact same way as before. Now, I did this to give you an idea of where all this information comes from. You can jump straight from figuring out what the pin name is and what the what port it belongs to this part, because once we know that the pin belonged to PTI par and that it was bit 1 of PTI, or once we knew that it was part of port TI and it was bit 1 of port TI, we could have jumped straight to this, because now we know that those variables, now we know that those variables exist, and we can just access them straight away. So that's it for this one. Let me know if you have any more questions, and I'll see you guys in class.